Hello, my name is Gabriela Ciocarlie. I'm with SRI International in New York City. We opened an office very recently. We are actually focusing on cybersecurity and analytics, so it's a perfect match for the workshop today. So I'm going to talk about security and reliability in infrastructure, in large infrastructure systems. So one of the interesting trends that is happening nowadays in industrial control systems is that there are a lot of targeted attacks that have been increasing in the past years, and there is a growing frequency in these attacks. And just so we know, there are at least 7,200 industrial control systems that are actually internet facing, and that number might be higher because it's an older number. More than that, industrial control systems sometimes rely on network cells. So network cells can also get different performance, degradation performance, not necessarily from attackers, but because of natural failures and so forth. So that can become an issue for other relying infrastructure. And finally, a lot of the critical infrastructure is moving to the cloud. We all know that moving to the cloud gives a lot of benefits, but security is not an immediate benefit. So sometimes the service level agreements might not include immediately procedures that allow somebody to actually track what's happening in the cloud. So all of these different large infrastructures are kind of, they have a common theme. It's not that easy to assess the security or reliability of them. So what is exactly the problem with the with data analytics for secure and reliable systems? So all the modern technologies are just generating so much data, much more data than sometimes we can actually access, and this is a process that is due to their actual functionality or is a byproduct of their operation. So sometimes it's intentional, sometimes it's just coming as a byproduct. And then the idea is, how can you use that data? A lot of data that is generated. You can do it either as an audit and monitor approach, or you can actually use that data to identify the intended behavior, kind of constrict the systems within the intended behavior. But analysis techniques, most of the time, what exists in the world nowadays relies more on signatures of what is a secure system, what is an attack, so that you can secure the system, or relies on signatures on new types of failure. So anomaly detection is kind of the approach where we can actually model systems based on all this data, and we can detect zero-day attacks or new types of failures and so forth. But of course, anomaly detection has its own issues. So real-time data can be polluted. So it's very, very hard to rely on data, and it's very, very hard to label data when we are talking about large systems. Systems change all the time, so you have to have mechanisms to adapt, and sometimes existing technologies are looking into the human in the loop to achieve that goal. False positives is another issue that sometimes anomaly detection techniques have, and then manual inspection is quite difficult to be produced. And last but not least, we have to have a way of keeping these anomaly detectors up to date. So I'm going to show you different approaches that I've taken in this area, and what were the benefits and what were the drawbacks to some extent in all of them. So anomaly detection, I've done a lot of work in the past on anomaly detection for large network systems. So I've analyzed network traffic, and the idea there was to actually train data based on all the traffic that I've seen in an enterprise network, and then to test network packets based on the models that I created. And packets can be classified either as normal or abnormal. And all this work was actually, actually I said that, what was the fundamental problem that I had in the past was that the quality of models can be quite, can raise quite significant issues. And sometimes the training data can have attacks that can actually either not intentionally, but sometimes intentionally can pollute a model and can lead to issues with a classification problem. So the goal of my work was to actually remove the training, to remove the attacks from the training data set so that we could actually build a real model of a real normal behavior. So I had a strategy where I was building these micro models within different times of within different periods of times, and then combine and have a large set of such micro models that were then used in a voting approach to actually test the traffic. And I used, so this technique was built on top of existing anomaly detectors. So I was improving the performance of two different anomaly detectors. And this is the data set, just to give you an idea of how many packets I had within a large enough time frame, and the types of attacks that were in focus at that time. And with this particular sanitization technique, where I was using the voting strategy to decide what packets are good and bad, I could achieve a significant improvement in the true positive rate, with some penalty in the false positive. What is in green is the sanitization part, and you can compare it with the rest of the non-sanitized models. So we can see that indeed both of these approaches, anagram and pale, were looking at bytecode. They were looking at bytes and looking at n-gram analysis within the content of a packet. So a very nice way of manipulating the content would actually reduce significantly the true positive rate of the sensors. By using the sanitization, we could actually improve them. Now, with all the techniques that we have out there, we always want to achieve automation. So the next goal of the work was to try to achieve this sanitization in an automated fashion. So trying to determine what are the parameters needed in the voting strategy automatically, and also to generate the voting threshold also automatically. These graphs are actually showing us for the two different types of sensors, anagram and pale, with different granularities at which the models were generated, what were the false positive and the detection rate. So we see, and what was the voting threshold, the V values there. So we see that there are sweet points for all different cases in which the granularity would have the best value. So the idea was to generate that in an automated fashion. So I looked at what is the likelihood of seeing new traffic, and that was the decision made of stopping a model and starting a new model and so forth. So that's how I was creating the different micro models. And then the voting threshold became a separation problem, where the idea was to find the smallest threshold that maximizes the level of normal data, so that I still have enough coverage of normality, but with a smallest threshold. So that approach actually enabled me to actually achieve the values, to determine the best values for voting. So overall, after applying these techniques, I was able to do to improve the true positive rate also empirically, like I showed earlier, but also in a fully automated fashion, and still achieve very, very good numbers. And this work has continued. And the whole goal was to also have cross-sanitization, so using multiple sensors, extending this in a distributed fashion, and trying to sanitize all these models by receiving models from other sites and sanitize based on that, and also doing the self-update where these models could be actually retrained over time in order to deal with the concept drift, with changes in the network. So this was some work that kind of showed when we talk about network traffic analysis, what are the types of things that we have to worry if we want a system that is automated. Now, in terms of control systems, industrial control systems, there is another aspect that is interesting here. So for industrial control systems, as I mentioned earlier, there are a lot of them in the US. You see a map there. Those are all internet-exposed industrial control systems. So there is a real risk. And one of the main issue in ICS is that they use specialized but insecure communication protocols. So that becomes a really big issue. And any kind of existing technologies for the enterprise level cannot be used in these environments because these protocols are very specific. But there is something that is in our advantage. ICS protocols, ICS environments have a fixed topology most of the time. Nowadays, they are moving towards more diversity, but still the control system will have a fixed topology. Regular communication patterns, limited numbers of protocols, and simple protocols. So that gives us an advantage in how we can model such systems, as opposed to the previous case where you could have a lot of diversity in how systems would interact with each other. So in terms of the connection model, you have a master and a slave. The master sends, you have a command with a parameter, and then you have the response coming back. That's kind of the idea. So quite simple settings. And now the question is how predictable is the behavior? How is the behavior? Is the behavior really predictable in an ICS network? So if we look globally across all the different devices communicating with each other, we might not be able to actually see that prediction. If we combine all the links on all the different protocols, devices, there will be a lot of change. If we look at the device level, a device can communicate with a lot of different devices on different protocols and at different frequencies and so forth. So that might be better, but not sufficient. What changes a lot is if we move at the connection level. So if we look at two devices communicating with each other, we can actually, that is the stable and deterministic part that we can model. So we actually modeled these connection level interactions by looking at the probability of seeing a certain command at a time tk given a system, a history of commands. So one way of doing that is to actually learn a Markov chain of order m. M is the history size. So there are a few things. You asked earlier about the quality of service. Sometimes, depending on the types of messages that are exchanged between different devices, you might have packets that can miss if we're talking about UDP and we are talking about not necessarily a reliable protocol communication. So reliability is not a quality of service per se. So these kind of issues can actually interfere a little bit with learning these patterns. So in our approach, we actually used probabilistic suffix trees as a variable order Markov model, and we were able to do that in an online fashion. So we changed a little bit the algorithm so that we had an incremental approach, right? We would not do batch learning, but we would do an incremental approach where we would update the tree as we see new types of elements communicated between the two. So just to give you an idea of a result, here we have a Modbus connection, and we have the near zero values are actually due to the missing packets that I was mentioning earlier. So those are all false positives. We know the ground truth of this data, and we knew that the data was normal. So we had to come up with a way in which we could compensate the false positives. So this is an example where if you have a missing sequence, then the probabilities can be quite messed up. So in this example, missing a 1 from there would cause a lot of false positives. So to address this issue, we came up with an incremental PST with prediction, where we would predict what would be normally the next sequence and use that to actually kind of insert that particular predicted sequence and see if the false positive rate is going to be improved. So these are the results on the same normal communications, and we can see that with a prediction we have a much lower false positive rate. And one question which is completely valid to ask is, what if an attacker is actually going to try to use this, right? An attacker can rely on sending commands that are completely normal, they look completely normal, but it can use this knowledge of inserting or changing the sequence, in a very special way to attack the system. To some extent, this is what the Stuxnet attack was, where every message was completely normal, but it's just the frequency at which messages were sent that actually had a physical impact on the centrifuge. So that's a valid question that I already put out there, and we are looking into ways in which we can address that from a game theory kind of approach. So overall, on real Modbus traffic, our approach also showed some improvements. So we have the 3 different approaches. We have a batch approach, we have the incremental one, and incremental with a prediction. In most cases, the incremental with a prediction approach showed the lowest false positive rate. So we were able to show that for these data sets that we knew were normal, we don't incur a huge false positive rate. And because it's very hard to get real data from this kind of very sensitive networks, we generated some synthetic data where we wanted to see what is the probability, or with a missing probability, or with an attack probability, how our results are impacted. So overall, as we see here, the detection rate is on the upper side and the false positive rate is on the lower side. And again, with the 3 different approaches, batch, incremental, and incremental with prediction, the incremental with prediction always did better. So there, it achieved higher values for the detection rate and lower values, low enough values for the false positive rate. And this is miss probability of 10%, so having a probability of missing packets, and here we have a miss probability of 50%. So even in a very bad case where you drop a lot of packets, the approaches are still showing good results. So overall, this was a new probabilistic suffix tree-based approach where we modeled the normal patterns of command and data sequences from industrial control systems. We have a way of reducing the false positive rate, and we have an actual implementation that worked also on real and simulated data sets. Again, this wanted to emphasize the fact that if you know a little bit more, if you are working in an environment which is much more predictive, then you can actually achieve interesting results. And now I'm switching to a different environment, cellular networks. Cellular networks, so I'm not looking at a security issue here. I'm actually looking at degradation. So when cellular networks, each individual cell has attached some metrics, key performance indicators. So these are the data points that we were analyzing with this work. And those key performance indicators are kind of saying how well each individual cell is doing. Now, when we talk about a network as a whole, one cell being misbehaving might not tell us too much. So I will try. So looking at a larger scale and looking at all the cells at once was something that was extremely important in this case, because we were looking at configurations. If you change the configurations within a full network, will the configuration will have a negative impact on the performance of the network or not? So the idea was to model the network and the sub-network overall state. And interestingly enough, we actually took an approach that might be a little bit surprising. So in analyzing text in NLP, there is this method called topic modeling, where people are applying them to actually extract topics within multiple documents that you might analyze. So we apply the same technique to actually extract states within a network based on all these key performance indicators. So we discovered the topics as states of a cellular network, depending on the different key performance indicators. And then we use the KPI characteristics. KPIs are drop call rate, call success rate. So these are the types of metrics that characterize a particular cell. We have a way of qualitatively say if a drop call rate or a call success rate is good or bad, and like this we could actually classify all the different topics that we extracted from the network. And then in the detection mode, we were able to say if the network is in a good state or in a bad state overall. So not going at individual cells, but going at a large scale. And then to be able to understand if the configuration changes had an actual impact. So to be able to diagnose if the network is doing not that great due to certain reasons, we actually use the Markov logic networks, which are which combine first order logic and probabilistic models in one representation. So imagine that you have rules, and each rule has a particular weight attached to it. So in the end, the MLNs compute the most likely explanation for an event in a data. I'll have to go quickly through this. So we combined the two approaches. One was for detection, the topic modeling for detection, the MLNs for the diagnosis, and we ran this on 9,000 cells. So we had a large data set. This is an example of a state. This would tell us that those two different KPIs are the ones that are actually not looking that great, and then this whole state would not be considered great based on that. And to give you a feel of what the outcome of the tool would be, given the different anomalies from the topic modeling, given changes, configuration changes in the system, we could actually say what cells were affected in the network by the push of configurations at the network level. And these were some results that showed us at what time there were the changes made and how they impacted, what was the percentage of cells that were impacted by it, and also weather can be sometimes quite a negative impact on cells. So that was another analysis that we've done to see how weather impacted the overall network performance. So to recap, I showed you 3 different environments with 3 different kind of needs. Some on security, some on fault detection. So new methods for detecting intrusions in an enterprise network. An approach that takes into consideration the industrial control systems environment characteristics, and a mobile broadband network approach that was modeling a network at a high level. So I will stop here. Thank you.
Any questions?
Thank you.
So I'm just curious about why you decided to use Markov logic networks.
Markov logic.
I know you have time to go into detail.
Yes. So we actually use them at SRI. We have a tool that is implementing MLNs, and we use them in other settings as well, and we were successful in doing so in analyzing how having vision techniques where you analyze when people are walking on a hallway or not walking on a hallway, so you could actually make certain reasonings around that. So we had quite great results there. So we experimented with a tool. It's very easy from a human perspective because it's very easy to write the rules in MLNs. So that's another reason we wanted to make a system that was easily usable, so that a human can actually insert a rule based on experience. So it had multiple good advantages.
Anybody else? She covered a lot of ground. Come on, somebody's got to have a question.
Well, I'm not sure I understood what the states were. When you use the NLP kind of algorithm to come up with topics, what were those? Just to help me understand what that.
So the states, again, the input to the network are the different KPIs, key performance indicators. So this would be a state, for example. These are, we were working with 9 different key performance indicators. So then a state would kind of say at a aggregate level, which key what is the state of the key performance indicators at that aggregated level. So in this case, those 2 marked in red, those 2 key performance indicators were not in a good state, so the portion of the network that was affected by that would be in this particular state.
Can you use this exact same method for the ICS network or anything else? You have less KPIs, but still.
Yes, definitely. I mean, this is something that we can definitely use. I didn't apply it because I've done this work in different time frames, but yeah, definitely.
All right. Everybody ready for lunch then?
Yes.
All right, so thank you very much.